talk about normal distributions. So distribution, what a distribution is, if you haven't already figured this out, is it's just a collection of variable responses. So if I were to go through the class and ask for everybody's weight, and everybody would give me, their weight in pounds probably, and I would write down all these weights, and I might bin them together in a frequency table, and I would take that information in the frequency table and I would chart something in a histogram because I'm talking about quantitative information, and that histogram might be unimodal symmetric, it might be bimodal and symmetric, it might be unimodal and skewed, it might be uniform. Whatever it is, that histogram represents a visual depiction of the distribution of weights in the class, of weights of people that I asked, how much do you weigh? All right. So that's what we're talking about with normal distributions, or at least as a distribution, that's what I'm talking about. So we're going to identify a specific type of distribution in this lecture, and that is the normal distribution. So here are the characteristics of a normal distribution. Number one, this is the big one, it's unimodal and symmetric. We think about, as we came up through high school, or even in your earlier college classes, people might talk about the bell curve. How grades are distributed might follow a bell curve. And what we have as a bell curve is literally a curve, let me just draw a baseline here, that has the shape of a bell. So if we're thinking about a histogram, what a normal distribution might look like as a histogram, well, it's going to be having its tallest bar centered in the middle, and then the shorter bars off to the left. As we go to extreme values to the left and to the right, those bars in the histogram are going to get smaller and smaller. All right, and we could see that it is a bell curve, because if we were to draw a curve over the tops of all these bars, it would look like a bell. Redraw the bell curve, and I apologize, my drawings aren't great. The second characteristic, not only are we unimodal and symmetric, but the center is always going to be at the data's mean. And this should make sense because in the previous chapters we said if we had a symmetric distribution and it was unimodal, then it was more appropriate to report the mean than the median. Now, I also said go ahead and do both since we're in a class, that's fine, but the more important statistic for center is the mean. So here, at the center of the distribution exists the mean. Now these normal models typically model a population, or these distributions model a population, so we want to talk about the population mean being at the center. And anytime we talk about population mean, we use the Greek letter mu to represent the population mean. So there is mu. Mu is the population mean. Another characteristic is that the spread, or the variability, is measured by the standard deviation. So this again should make sense because previously we said if we had a unimodal symmetric distribution, we would prefer to use the standard deviation, whereas if we had a skewed distribution, we were going to use either the IQR or the range, depending on whether or not we had outliers. All right, but here we're going to use the standard deviation, and again we're talking about a population standard deviation. So when we talk about population standard deviation, we're using a lowercase sigma. All right, that's the population standard deviation. And before I get to number 4, let me go ahead and define all of these values that we're going to start using here in Chapter 5. We've already defined, I accidentally hit a button there, we've already defined mu as the population mean, so the population mean. And we've already defined lowercase sigma as the population standard deviation. And there are going to be a couple other values that we're going to look at in this, or letters that we're going to look at here. We're going to look at y bar. Sometimes it's x bar, but that's going to be a sample mean. And lowercase s would represent the sample standard deviation. So when we go in, we calculate the standard deviation previously for those previous assignments, and we've done this in Excel, and we've highlighted those data, and we've gone to the STDEV calculation in Excel. That's calculating the sample standard deviation more likely than not. All right. So there we go. The final characteristic. These normal distributions, these normal models, are approximated with the 68, 95, 99.7% rule. And I believe I have a previous lecture video where the woman describes it as an empirical rule. Same thing, though, okay? And what this rule states is that 68% of the data in a distribution is going to be within one standard deviation of the mean. So what does that mean? Well, within one standard deviation of the mean means we could go below the mean one standard deviation, and we could go above the mean one standard deviation, and we could say that, all right, between those two markers, that's within one standard deviation of the center, the mean, then 68% of all of the data in a normal distribution exists between those 2 points. All right. For example, if I were asking for everybody's weights in the class, then I have a population of weights in a 241 online statistics class. If these weights followed a normal distribution, then 68% of all the weights that I surveyed in this class should be between one standard deviation below the average weight and one standard deviation above the average weight, if in fact we have a normal distribution. Then we can go on, and I wish I could, I don't know if I can do different colors here, but it would be amazing if I could. It doesn't look like I can. But we can go on and say, make sure I turn my pen on again, 68% is between one standard deviation of the, or within one standard deviation of the mean. Then 95% of the data is actually between two standard deviations, or within two standard deviations of the mean. What am I doing? Let's see. Can I Control Z this? Let's see. See, this is the problem when I get to technology. One little mess up and everything goes nuts, and I don't know how to take it back. Let's try Control minus. That works. All right. So we had 68% within one standard deviation, and we can also say that 95% of the data is within two standard deviations. And maybe, just maybe, I'll be able to write with my pen. Oh, for crying out loud. There we go. 95% are within two standard deviations. So here's a second standard deviation below, and here's a second standard deviation above. And 95% of the data in the distribution should be between those 2 points. So, you know, again, I would have a list of weights. I'd be able to calculate the average weight, and that weight would go in the center. Then I would be able to calculate a standard deviation of those weights, and I would add that to the center to get a marker for one standard deviation above. I would subtract it from the center to get to the mark one standard deviation below, and then I could add two standard deviations to get the weight that would represent two standard deviations above, and then subtract it from the center to get two standard deviations below. But 95% of all the weights in this class, if we follow a normal model, will be between those two standard deviation markers. And then lastly, I think you can see the pattern here. If we look at this 99.7, that says that 99.7% of all of the values in a normal distribution, all the data in a normal distribution, fall within three standard deviations. So 3 below and 3 above. 99.5 or 0.7 rather, 99.7% of all the data fall between those markers. All right. And this makes sense, you know, as we go farther and farther out, we're encompassing more and more and more of our bell curve, of our histogram, more and more data, so we should have a higher amount of data within these intervals. We should have even more data existing between within 4 standard deviations of the mean. Probably like 99.999999999% of the data is within 4 standard deviations, and then 99.99999999999 is within 5 standard deviations, so on and so forth. But what we can see is very little information is left in the tails. In fact, after 3 standard deviations from the mean, we only have 0.3% of all of the remaining data existing here in these tails. All right. And it's worth noting, again, this is a symmetric distribution. So there should be an equal amount left in this tail as there is in this tail. All right. So let me go back and let me go to the next slide. And again, let's draw a generic model using the 68, 95, 99% rule. But what we can do is we can divide these into more specific intervals. Alright, so here's the center. Here is 1 standard deviation above. Here is 2 standard deviations above. Here is 3 above. 3 above. And then we have 1, computer's so touchy, 1 standard deviation below. Oh, come on, stop. 1 standard deviation below, 2 standard deviations below, and 3 standard deviations below. And what we said is that 68% of the data exists between or within 1 standard deviation of the mean, or between 1 standard deviation below the mean and 1 standard deviation above the mean. 68% of the data exists between those 2 markers. All right, but how much of the data exists between the center and 1 standard deviation above? All right, how much data exists in this region? Well, it's a symmetric distribution. So if we have 68% between 1 standard deviation below and 1 standard deviation above, and it's a symmetric distribution, then each of these segments, this segment here, should have as much data in this one, so they should both be half of 68%. So let me take away those. Half of 68% is 34%. So 34% of the data exists in that interval, and 34% of the data exists in that interval. All right. We also know that 95% of the data exists within 2 standard deviations. So from here, please stop messing me up, computer. Exists from 2 standard deviations below to 2 above. That's 95% of the data. And 68% of that 95% exists in this area. So what's left over is 95 minus 68. Well, what's 95 minus 68? It's 95 minus 68 is 23? 95. I should probably get a calculator out. It's too early for me to do calculations. 95 minus 68 is 27, so way off. It's 27% exists in these 2 segments. Right here and right here represent 27% of the data. And again, it's symmetric. Therefore, half of the 27% is in this area, and half of the 27% is in that area. So what is half of 27%? It's 13.5%. 13.5%. 13.5. Make sure you're listening as I'm writing, just so you don't confuse that with a 15.5. It's 13.5%. All right. Now, how much information exists? We'll skip that one. Let's go into the tails. How much information exists in the tails? We've already talked about this. So 99.7% of the data in this distribution exists within 3 standard deviations. And remember, the whole distribution encompasses the whole data, so the whole distribution is 100% of the data. This encompasses 99.7%, so the remaining 3% is in the tails, and they're split evenly between the left tail and the right tail. So half of 0.3% is 0.15%. So we have 0.15% in that tail and 0.15% in that tail. 0.15. All right. And 0.35 in this section right here. 2.35% of the data there. 2.35% of the data there. Now this is a much better drawing in the book, which is why I always have you guys read the book, because I can't draw with the stylus, especially with the computer messing me up all the time. But this is how we can kind of, operate with the 68, 95, 99% rule. And what we do is we try to estimate percentage of data based on certain scores in this model. These are questions that we can answer based on the model, based on the 68, 95, 99.7% rule. So at the very least, if you're taking notes on this, you want a model with the 68, 95, 99.7 intervals, and then you probably want another picture with those intervals broken up as we see here on the screen, the 34 and 34, the 13.5, 13.5, the 2.35, the 2.35, and the 0.15. So you can see how much or what percent of the data in the distribution exists within each of those smaller intervals. All right.